Alright, now I'm going to finish going over selected problems from section 4.4a, and let's start with 23. Okay, so 23 is finding the definite integral of the absolute value of 2x minus 3 from 0 to 3. Now there's two ways that we can approach find the definite integral of an absolute value function. First is geometric method. Okay, what's going to happen is if we have absolute value function, it's always going to produce a graph that's either a v that's right side up or a v that is upside down, and it's going to produce straight lines, and we're essentially, if we can identify the triangles that's produced, then we can just use geometric method, use area, add the areas of triangles to find the definite integral for that region. Okay, so let me go through that first. We can do that by first sketching the graph. This is, if we think about it in the form of absolute value of x minus h plus k, if we can figure out what will make this value 0, then that will be the x value, and whatever is outside will be the k value, so or the vertex, the order pair for the vertex. Right. So if I set 2x minus 3 equal to 0, I'm going to get 3 over 2, or 1.5. There's no value outside the parentheses or outside the brackets, so we know the k value is 0. So we know that our vertex is going to exist for the graph at 3 halves 0. Okay, or 1.50. Okay. We know the graph is going to be right side up because we have a positive a value. So you can plot your vertex at 3 halves 0, and then we're going to have two lines, and these two lines are basically going to be a positive, the original function that as you see it, 2x minus 3, and then also the negative version of the original line. So in this case, negative parentheses 2x minus 3, so therefore negative 2x plus 3. Okay. If we can find the ordered pairs at the left and the right endpoint, then we can find the height of each of these triangles, and then from there we can find the area of the two triangles and add them together. So if I plug 0 into my left graph, I'm going to get a positive 3. So if I plot that point there, this also will represent the height of my first triangle. And my right endpoint is 3, so if I plug 3 into the 2x minus 3, I'm going to get a y value of 3. So I can now easily find the area of these two triangles, and if I add them up, then I'm going to find the definite integral of my absolute value function. So my area is simply 1/2 base times height, so 1/2 3 halves times 3, that's 9/4. My second triangle, 1/2 base times height, 1/2 base is 1.5, and my height is 3, so 1/2 3 halves times 3 gives me 9/4 as well. Add these together, and we're going to get 18/4 or 9 halves. Okay. Another way that we can do this is using the integral method. So we still need to find our vertex, which is 3 halves. We still need to graph, at least give a basic sketch. We still need to identify that these are two linear equations. So what I can do is I can use integral method and find the definite integral from 0 to 2 for my function negative 2x minus 3. And then separately find the definite integral from 1.5 to 3 for my function 2x minus 3, because now my second curve is, for this region, is 2x minus 3. Okay, I can go through power rule here. So for my first definite integral, go through power rule, I get negative 2x squared over 2 plus 3x. Evaluate between my upper and lower bound, plug 1.5 into my function here. I'm going to get negative 1.5 squared plus 3 times 1.5. Plug 0 into my my lower bound into my function. I'm going to get 0. So all this comes out to be 2.25. So this definite integral for my first region is 2.25. For my right definite integral is 2x minus 3, so find a definite integral. I'm going to get 2x squared over 2 minus 3x. Evaluate between my upper and lower bound, and plug 3 in first. I get 9 minus 9. Plug in my lower bound next. I'm going to get 1.5 squared minus 3 times 1.5. All this comes out to be negative times a negative 2.25, which is 2.25. I add my two definite integrals together. I'm going to get 4.5 over 9 halves. And as you can see, that does equal the value that we found using the geometric method. All right, 25. Find a definite integral of absolute value of x squared minus 4. Okay, so it helps if we can graph this function. So here's x squared minus 4. We know this is a parabola that will have a vertex at 0, negative 4. So here's our graph here. But we're only interested in finding the definite integral from 0 to 3. So we have portions that's below the x-axis. The graph will cross the x-axis at 2, and then there's going to be portions between 2 and 3 that is above the x-axis. All right. So we can find, therefore, if we find the definite integral from 0 to 2 for x squared minus 4, this will produce the area, this will produce a definite integral that will be negative, right? But it's asking for the absolute value of this region, so I can put a negative in front to guarantee that this will produce a positive value. And then I can separately find the definite integral from 2 to 3, and that will give me this region. This is above the x-axis, so I know that will give me a positive value. Okay, so we go through our integral process, integral steps. X cubed over 3 minus 4x, evaluate between upper and lower bound. All this will give us 8/3 minus 8 minus 0, which is negative 16/3, but we're going to make it positive because this is absolute value. Okay, for the second region, find a definite integral, x cubed over 3 minus 4x. Evaluate between your upper and lower bound, plug in 3, we're going to get 27 over 3 minus 12, minus, then plug in your lower bound, 8/3 minus 8. Combine this, we get 7/3, so 16/3 plus 7/3 will give me a definite integral of 23 over 3. Okay, 27. These are just going to be trig problems that we have to find the definite integral for. So the definite integral for 1 plus sine of x, we know 1 using power rule becomes x, sine x becomes negative cosine x. Evaluate between your upper and lower bound, plug pi into x minus cosine x, we get pi minus cosine of pi. That represents f of b, minus, okay, that's part of first theorem of calculus. Then plug in the lower bound, 0 in for x, 0 in for cosine of 0. So pi minus negative 1 minus 0 minus cosine of 0, which is 1. The two negatives cancel out to be positive, so pi plus 1 is pi plus 2. Okay, 29. Integral of secant squared x is simply tangent x. Evaluate between upper and lower bound. Plug pi over 6 in for tangent x. Plug negative pi over 6 in for x. Tan of pi over 6 is 1 over root 3. Tangent negative pi over 6 is negative 1 over root 3. But there's a minus in between. The two negatives cancel out, and we're going to get 2 over root 3 or 2 root 3 over 3. Okay, 31. For secant tangent, we know secant tangent becomes secant theta. The 4 is the coefficient, that's just going to stay there. Evaluate between your upper and lower bound, plug pi over 3 in for theta. Okay. All secant of pi over 3 will produce 2. Then we do minus, plug the lower bound in for theta, so 4 secant negative pi over 3. Secant of negative pi over 3 also produces 2, so 8 minus 8 will give us 0.